Hello. In this talk, I'm going to share my recent work with Ali Mohammed and Niels Martin Muller. And the title of this talk is Entropy Bounds for Embedded Self-Shrinkers with Rotational Symmetries. So I, Ali, and Niels, we are both from the University of Copenhagen. I am a postdoc there, and Ali is a PhD student of Niels. So this talk will be split into two parts. In the first part, I will recall what is the definition of self-shrinkers, what are some very basic properties, and I will discuss in particular self-shrinkers that are rotationally symmetric, and that will be the first part of this seminar. And then in the second part, I will discuss the recent work that we did. Okay, so first recall what is a mean curvature flow. Well, if we are given a family of immersed hypersurface in the Euclidean space, then we say that this family, we call this MT. T is time parameters. So we call this a mean curvature flow if the mean curvature, if the immersed hypersurface move along the mean curvature vectors. That means if you take the derivative of the motion with respect to t, and then you take the normal components, that equals exactly the mean curvature vectors. An object that is highly related to mean curvature flow is what we call self-shrinker, which is a hypersurface in the Euclidean space which satisfies this equality. That's the mean curvature vector is -1/2 of the orthogonal parts of the positional vectors. You can see a picture here. This is one example of a self-shrinker. This is a cylinder. As you can see that I can think of any point in the cylinder as a position vector, and then I take the negative, and then I take the 1/2, and then I consider only the orthogonal part. If that equals exactly the mean curvature vector, that will be the self-shrinkers. With the suitable choice of the radius of this cylinder, we can make it a self-shrinker. Self-shrinkers are related to the mean curvature flow. Well, because first of all, if you are given a self-shrinkers, then you can use it to construct a solution to the mean curvature flow equation given by sigma t, which equals square root of -t times sigma. This is just a scaling of the original sigma, and the motion is of the mean curvature flow in this case is just the scaling. But more importantly, self-shrinkers models singularities in the sense that when you have mean curvature flow which is not defined at a time capital T, and we know that at that time the norm of the second fundamental form blows up, and depends on what we call type 1 or type 2 singularities. Huelsken was first shown in the 1990s that under rescaling at the singularity, it converged, the flow converged to a self-shrinkers. And later, it was done by Emanen and White that the same is true for general singularities, but with a weaker convergence to the self-shrinkers. So I will give some examples of self-shrinkers. We start with the lowest dimension. That means we're dealing with curves in R2. In that case, all the compact examples has been classified a long time ago by Ambrose and Lena. And they have an infinite family, a countable family of examples, and these are three of the examples, and they're all convex in the sense that the curvature is always positive. And amongst all these examples, the shrinking circle is the only one that is embedded. So this is a one-dimensional case. In higher dimension, there are sort of two directions. The first one is called the Angenent doughnuts. We'll talk about that later on. And then we also have a bunch of numerical examples that I did not discuss in this talk. But there's another construction done rather recently for the past 10 years by these two groups of mathematicians, Kapelas, Klein, Mona, and Gruen. So what they do is that they take the plane and the sphere, and then they take the Eulian. This doesn't give you an embedded self-shrinker, but they have a desingularization process that is done by gluing finitely many holes between these two self-shrinkers and make it into an embedded one. In their construction, they're able to construct such a self-shrinkers for any high genus. And more recently, another group, well, very recently actually, another group of mathematicians, Bolzano, Gruen, and Suess, they use the min-max theory to construct non-compact embedded examples, but now with every genus. And these are the pictures that I take from the archive preprints. And in these examples, in these pictures, we have surface of genus 1, 2, and 3 respectively. Okay, so now I want to discuss some rigidity and compactness results about self-shrinkers. But before that, I want to introduce this well-known characterization. We know that sigma is a self-shrinker if and only if sigma is a critical value of this F functional, which is the same as saying that sigma is a minimal surface with respect to this conformal metric, the one given by multiply the Euclidean metric by e to the negative x squared over 2n. Okay, and if you think of this as a minimal surface, then it's checked by Kolding and Minicozzi that all self-shrinkers are actually unstable. That means I'm taking the second variation of the F functional, and it turns out that they're all unstable. And the unstable direction is given by, at least given by the scaling and also the translation. In order to deal with these two unstable direction, they Kolding and Minicozzi define this entropy, which is the F functional of all possible scaling and translation of your surface sigma. And using that, they define a notion of entropy stability. Okay, I'm not going to define it, but basically it's a stability condition that is marking out this too long unstable direction. And they're able to show this very nice theorem. They show that amongst all self-shrinkers, only the generalized cylinders entropy stable. Okay, so it includes the hyperplane, which is when k equals 0, and it also includes the sphere when k equals n. Okay. The entropy, as you can see, is taking like supremum of this F functional. But I want to point out that in the case of self-shrinker, Kolding and Minicozzi also check that the supremum is actually attained at the self-shrinker, so you don't need to do any translation and scaling. We're going to use that later on in part 2 of this lecture. Okay, so I want to give some examples of the rigidity and compactness. There are many examples, but among that, there are two very nice results. The first one by Rang, it shows that if you're given an asymptotically a cone, then there's only one self-shrinker that has an n that is asymptotic to this cone. So that means that simplifies the classification result of the classification problem of asymptotically conical self-string lots, because you need only to classify all this cone. Another result particularly holds for this 3-dimension is the a very nice result by Brendel. It shows that the only genus 0 embedded self-stringers in R3 are the sphere, the cylinder, and the plane. Okay. In general, we don't have, well, besides these two results, in general, we don't have such a nice rigidity result, but we do have two very nice compactness results about embedded self-stringing surface in R3. The first one is by Coding and Minicozzi, where they assume that we have the space of bounded entropy and bounded genus self-stringers in R3. Okay, and they show a smooth compactness result. That means if you have a sequence of embedded self-stringing surface in R3 with bounded genus and bounded entropy, then you can extract a convergence subsequence, and the convergence is locally smooth, graphical. Okay, and quite recently, this result was generalized by Sun and Wang in 2020. So instead of a bounded genus, they're able to prove the same compactness result for fixed genus. That means you cannot have, for example, a genus, a sequence of genus 1 self-stringer converging locally smoothly to a cylinder, for example. Okay, so in the second part of this first introduction, we will specialize in rotational symmetric self-stringers. So a hypersurface sigma in the Euclidean space is rotational symmetric with the axis L if it is invariant under all rotation fixing the axis L. Okay, and it's sort of clear that any rotational symmetric hypersurface is determined by this cross section. Actually, it's half of the cross section where we call the profile curve. So we take any hypersurface, any two plane containing the axis L, and then we take the intersection of this rotational symmetric hypersurface with that plane, and that will give us part of this, half of it will give us the profile curve. Okay, so this is one example of the profile curve on the left, given by this sigma colored in red in the upper half plane H. And if you rotate it, that will give you the rotational symmetric hypersurface. So in this special situation, we have the following characterization. So this sigma sigma, this notation means that we have a rotational symmetric hypersurface given by the profile curve sigma. Okay, so if sigma sigma is a self-stringer, then this is true if and only if after reparametrization, this sigma is a geodesic in this Riemannian manifold H with the metric GA. GA here is called the Angenent metric given by this formula. So it's conformal metric to the Euclidean, standard Euclidean metric. This is just a direct checking. And in that case, the entropy is also related to the geodesic length, the length of the geodesic sigma given by this formula. In this formula, omega n-1 is the volume of the n-1 unit stream. Okay, well, if you consider only rotational symmetric self-stringers, then instead of the original equation, which is second order elliptic equations, we we simplify it into just a geodesic equation, which is just a second order ODE. And because of that, we can apply ODE method to construct examples. And this is exactly what Angenent did in 1989. So he considered this shooting method. So this is the upper half plane. And he starts with any curve starting at the R axis and going out horizontally. And the hope is that he wants to find one curve that is hitting the R axis again horizontally. If you're able to do that, then we can reflect this this curve to give a smooth, simple closed geodesic in the Angenent space, and that will give us one embedded examples. And this is exactly what Angenent did to construct what we call the Angenent doughnuts. So the doughnuts that Angenent construct has convex profile curve, and by construction, this curve is also symmetric with respect to the R-axis. Okay. So if we don't care about embeddedness, then there's actually much more example, actually infinitely many more examples that are constructed by Duran and Duran-Keeney using the same shooting method. Sometimes they will shoot again from the R-axis, but in some cases they also shoot from the X-axis. Okay, so these are 4 examples that were constructed by them in these 2 papers. So the one on the upper left, if you rotate it along the X-axis, that will give us an immersed S2. The one on the upper right gives us an immersed torus. The one at the lower left gives us an immersed cylinder, and the last one gives us an immersed R2. Okay, so if you consider only immersed, also immersed in examples, there's actually infinitely many of them. Okay, so concerning the space of all these rotational symmetric self-shrinkers, up to this moment, the only known example is the Angenent doughnuts, and the conjecture is that at least when n equals 2, the Angenent doughnuts is the only compact rotational symmetric self-shrinking example. Genus 1 example. Of course, we have the sphere, which is also rotational symmetric. Okay. I want to point out that there are other construction of embedded self-shrinking doughnuts given by Duran and Gurin using another method, using geometric flow. But it is not clear if the example that they construct is or is not the same as the one constructed by Angenent. So it's not really clear if we have more than one example, although we have 2 different constructions. Okay, so the bigger problem is that it's the Angenent torus, the only compact embedded genus 1 examples in R3. This is as of now completely open. But this is, well, these 2 open questions are sort of the guiding problem for us to study the space of all these self-shrinkers. So before I end, I want to discuss several known results about all these rotational symmetric self-shrinkers. So the first one is this partial classification result by Pili and Mona in 2017. So if they show that in any dimension n, if sigma sigma is complete embedded, then it can only be this four results, these four examples: the hyperplane, the round sphere, and the round cylinder. Okay, the last one is sort of unknown. So we know the last one we say that is only diffeomorphic to S1 cos Sn minus 1. So so we call this a partial classification. So because for the last part, number 4, we don't exactly know how many such examples in number 4 are there. Okay, so in this picture, this is an illustration of all these examples. P is the hyperplane. We also think of it as the R-axis, which is rotationally symmetric, and also the round sphere given by yellow, and also the cylinder, which is in green. And all the other examples I just draw it as red. Okay. Besides this partial classification, we also have this compactness theorem proved very recently by Rama. They say the following. So the first theorem is that the space of all such rotationally symmetric embedded self-shrinker with entropy strictly smaller than 2, or to be precise, strictly smaller than lambda, where lambda is strictly smaller than 2. If we consider such space of self-shrinkers, then this is compact, smoothly compact. On the other hand, if instead of entropy, if we assume the convexity of the profile curves, then he also showed a compactness result when n is bigger than or equals to 3. The techniques that he used were mainly that from minimal surface. In particular, he used essentially the fact that the only rotationally symmetric minimal surface in R3 is the cagnoid. Okay. So, but beside that, so we don't have any other compactness results. And in the second part, we will describe our recent work, which is mainly a generalization, well, which is first of all an a priori bound on the entropy of such a self-shrinker. And the second part, as an application, we actually were able to generalize the results by Rama proof in 2021. Okay, so that's the end of the first part.